we can classify materials by how well they conduct, or allow electrical current to pass through them. For example, we have conductors, which include most metals and allow current to flow through them very easily. Examples of conductors include gold, silver, steel, and even seawater. We also have electrical insulators, and electrical current can't flow through these. Rubber, diamond, oil, and glass are all examples of electrical insulators. There exists a third category of material, where we talk about semiconductors, which can conduct, but only in certain circumstances. So what is a semiconductor? An example of a semiconductor is silicon. Silicon has 4 electrons in its outermost electron shell, sometimes known as a valence shell. A silicon atom can share one of its outermost or valence electrons with a neighbouring silicon atom. When this happens, this is known as a covalent bond. When a silicon atom is surrounded by 4 other silicon atoms in a crystal lattice, it has access to 8 outer electrons. Current cannot flow through a silicon crystal in a situation like this, because there's nowhere for charge to move. We can help silicon conduct by a process called doping, where elements other than silicon are introduced into the silicon crystal. These foreign elements are called dopants. A commonly used dopant is arsenic, which has 5 outer electrons in its valence shell, so 1 extra compared to silicon, which has 4. If arsenic is introduced into a silicon lattice, this results in a free electron in the lattice structure, which isn't associated with or bound to 1 atom and is free to move. This free electron allows charge flow through the semiconductor. When a free electron is introduced into a semiconductor lattice, this is known as an N-type semiconductor, where the charge carriers are negatively charged electrons. Silicon can also be doped with elements like boron, which have 3 outer electrons, or 1 less than silicon. The gap due to the missing electron is called a hole, which has a slight positive charge. In a lattice, this hole means that there is space for electrons to move. This means that it is possible for current to flow. When a hole is introduced in a lattice, this is known as a p-type semiconductor, due to the slight positive charge of the hole. So what happens next? We can take one silicon crystal, where one side has been doped such that it is a p-type semiconductor, and another side such that it is an n-type semiconductor. The interface between the two of these is known as a p-n junction. A p-n junction is an example of a diode. Current can only flow through it one way. At the p-n junction, the free electrons in the n-type semiconductor diffuse towards the p-type semiconductor, where they combine with holes. This leads to a positive charge at the n-type and an equal negative charge at the p-type. The region containing the charges is known as the depletion layer. If we apply positive potential to the p-type and negative potential to the n-type, the depletion layer is closed and current can flow. This is known as forward bias. On the other hand, if we apply negative potential to the p-type and positive potential to the n-type, the depletion layer is widened and current cannot flow. This is known as reverse bias. If we keep increasing the reverse bias across the p-n junction, eventually we reach a point known as electrical breakdown, where the diode can start to conduct. The voltage at which this happens is called the electrical breakdown voltage. Most diodes will be irreparably damaged by this, but some are designed to operate above the breakdown voltage. The single photon avalanche diode, or SPAD, is one of these diodes and can be used to detect light. A SPAD is a p-n junction operating above its breakdown voltage. In a SPAD, a photon can be absorbed in the silicon and knock an electron or hole out of the crystal lattice. This electron gains energy due to the electric field at the p-n junction and can knock other electrons out in a process known as impact ionization. These gain energy in the same way, ionizing more atoms in a sort of chain reaction known as an avalanche. One photon usually causes the release of around 1 million electrons. This results in a charge pulse, which we can use electronics to collect and measure with fast timing. We can connect SPADs in parallel, pack them closely together to make a larger detector called a silicon photomultiplier, or SIPM. These high-tech detectors are able to detect very low levels of light, sensitive to down to just 1 photon. So what can we use these for? SIPMs are used for lots of things, though they're a relatively new technology. They can detect low levels of light very quickly, so are used in a technology known as LiDAR. This stands for Light Detection and Imaging, where a laser is fired at an object and the time taken for it to reflect and return to a sensor is used to work out how far away the object is. This has applications for self-driving cars or even imaging the bottom of the ocean. SIPMs are also used in medicine, in various medical imaging applications. In physics, SIPMs will be used to solve the mysteries of the universe, for example, in large experiments searching for dark matter, and could be used in telescopes sent into space, among many other things. The future for SIPMs is bright, especially when light levels are low.